Hey everyone, welcome to the narration of my poster. So if you are not super into reading, I'm going to read to you. This is for the online hybrid portion of the poster. If you want, within the next 2 hours, I'm going to be presenting over the poster hall, but I'm guessing by the time that this is posted, that's probably already over. But I really appreciate you coming. Right now, if you're watching this, you're in some way interested in my poster, so I appreciate it. My name's Eric Agliano. I work with David Sheen, Scott Henderson, and Seth Vanderwalt. The title of my poster is Capturing the Evolution of Mountain Snow in the Western U.S. using Synthetic Aperture Radar. And my contact info is right up there, my email address, and my Twitter that I definitely use all the time. And I'm in the Terrain Analysis and Cryosphere Observation Lab, which is in the Civil and Environmental Engineering Department at the University of Washington. So I'm going to start reading to you. So the abstract says, this work focuses on capturing the spatial and temporal variability of snowmelt timing in mountain environments using synthetic aperture radar, or SAR. While the analysis in this poster focuses on Mount Rainier for 1 year, we built our analysis on scalable tools for future time series comparisons between similar mountain environments. The motivation is that mountain snow is very important for water supply, so drinking water, agriculture, that type of thing, as well as hazards, so things like landslides and runoff contamination. Snowmelt is highly variable in space and time, and capturing this variation can improve water forecasting as well as hazard forecasting because of it. Additionally, knowledge of snowmelt variability over glaciers can help us improve our understanding of glacier mass balance, as well as water delivered to the bed, which has important implications with lubrication and glacier velocities. So for the methods section, to capture snowmelt runoff onset, we calculate the minima of a SAR backscatter time series, as described in this wonderful paper that this figure is from. So what we do, though, is we estimate the spatial variability of snowmelt by calculating these minima pixel-wise. So going pixel by pixel, and for our entire time series, calculating the minima. And additionally, we investigate the controls on snowmelt timing using a regression analysis. So we'll look at two factors that we'll talk about soon against our snowmelt runoff onset date map that we produce using the SAR backscatter minima in our time series. And in the bottom left here, we can see that our data is over Mount Rainier, and we've resampled monthly these three different sets of data just for purposes of viewing. The actual data that we use in our backscatter minima algorithm is not resampled, but this is just for ease of comparison in terms of RGB on the left, what we see visually, then an NDSI or a normalized difference snow index, basically a map of where the snow is, and then our SAR on the right-hand side. So let's look at the main figure of the poster in the middle top, snowmelt runoff onset date. So we see a day of year SAR-derived runoff onset date for the year 2020. These darker blues are going to represent earlier in the year, and the yellows are going to be later in the year. So right off the bat, we see that we get more yellow colors, more brighter colors as we go up the mountain, as we would expect, because we expect higher elevations means colder temperatures, which mean snowmelt runoff onset date will be later. Snowmelt runoff onset is the point at which the snow becomes super saturated and the water actually starts to run off from the snowpack. That's a very important date for hydrologists, as well as people worried about hazards. So if we look on the right-hand side now, the backscatter time series binned by elevation, we get a clearer picture of how elevation plays a role in all of this. The brighter colors are higher backscatter, and the darker colors are the lower backscatter. And so whenever we hit that backscatter minimum, that's when we are predicting that the snowmelt begins. So for example, for the 1,000 to 1,500 meter bin, we see that the darkest colors, the darkest black / purplish, is the beginning of April. So we believe that in the 1,000 to 1,500 meter band, that the runoff starts in April. And we can validate this because we also have right beneath this plot, a backscatter time series for the entire area of interest, as well as Sentinel-2 NDSI and Sentinel-2 all-band average time series. This is also paired with some SNOWTEL data, SNOWTEL site number 679, which is in Paradise, Washington. So we see SWE, snow water equivalent, as well as snow depth. And we have the time series here. And just for a quick validation, we know that this SNOWTEL site is at an elevation of 1,564 meters. So if we go to our 1,500 to 2,000 meter band, where we know that this SNOWTEL site exists, it predicts that we would give our snowmelt runoff onset date in the beginning of April. And if we go straight down, drawing a straight down line, we see that SWE actually begins to decrease during this time, as well as snow depth. So we know that when these two values start to decrease, that's when the runoff onset's beginning. So this gives us a little bit of validation and confidence in our results that this SAR backscatter time series minima is producing accurate maps of when the runoff is beginning. So now moving on to snowmelt runoff onset over glaciers. We talked about in motivation why this is important to know, but now we're kind of removing elevation from the equation. We're just looking at specific glaciers. And again, we see on the left-hand side here, some glacier polygons, the extent of some glaciers, and those colors correspond to their mean backscatter in the plot to the right of it. The dark blue star here is our SNOWTEL site where we collected the SWE, and we can see the SWE overlaid in the blue, just as it was overlaid in the blue in the plot above. And this shows us that the response of the glaciers are all pretty similar in the fact that they seem to hit their minima in the beginning of May, which is consistent with what we know. And we see that they all behave relatively similarly. There's some differences because we know that aspect may play a role in terms of timing, as well as the weightings of different glaciers are going to be different because some glaciers have more area in higher elevations and some in lower elevations. So we would expect ones in higher elevations to respond differently in terms of backscatter and when the mean is melting. Again, these are just averaged values over the entire glacier. But again, we see similar results as before. Whenever the SWE starts to decrease, we see the decrease as well in backscatter. And we see a little bit of a delay, but again, that's because of the elevation differences of the SNOWTEL site and the average elevations of these glaciers. We can also see that once the snow has disappeared in August, as things dry up, we see our backscatter go up. And then once accumulation starts in November, we see some more marked increases in backscatter, which is consistent with what we know. So now we are going to see how much of an effect elevation plays in the snowmelt runoff onset date timing. So on the left, we have our digital elevation model, which is going to tell us about our elevation. And then on the right-hand side is what we're using as a proxy for shortwave radiation exposure. So how much sunlight basically is something getting. And that's the diurnal anisotropic heating, or we'll call DAH index. So these are the two inputs that we're using to a regression analysis. And when we run the regression analysis, these two factors account for 33.4% of the variance in SAR-derived runoff onset dates, so a decent chunk of the variance. I think we expected a little bit higher numbers here, so that's going to be something fun in the future to investigate. What are the other controls on runoff onset date timing? But as you can see on the left-hand side, we have a map of the runoff onset dates. So darker blues are in February, and the brighter whites are the end of July. And right next to it, we have the predicted from just elevation and DAH index alone. And we can see it does decently well. This analysis tells us, though, that for every 100 meters of elevation gain, there's about a 4.28 day later predicted runoff onset date. And the final takeaway from this is that SAR is really powerful for assessing the evolution of mountain snow. And once we combine it more formally with the Sentinel-2 and also probably Landsat 8 data, optical data, multispectral data, we'll have some better results for predicting these onset dates. So for next steps, it says here that we are going to do more systematic analyses and comparisons of similar mountain environments. We're going to formalize the method for fusing the SAR data and the optical imagery data for predicting melt timings. And then MODIS also has a snow melt product, so exploring some fusion with that, even though they're at much coarser resolutions. And also looking at validating runoff onset date results with stream gauge data. This is probably not as fair for Mount Rainier, because we know that the stream gauge data tends to be downstream of dams, which isn't really a fair comparison. So perhaps on Mount Baker or somewhere else with some good stream gauges, we can do some comparisons to really validate that we're capturing the right snowmelt runoff onset date. We'd also like to compare across other snow environments, such as tundra, to see how snow responds differently in these different environments. And we'd like to investigate the snowmelt implications for glacier mass balance, study the effect of glacier debris cover on our analyses, because when we were trying to predict some ripening dates, so which is the stage right before runoff, as water is accumulating in the snowpack, we noticed some glacier debris artifacts in calculating those values. So we think we can learn something about glacier debris, or at least we can mask it out to continue our analyses. And finally, we'd like to delineate between the different snowmelt phases. So looking at the derivative backscatter for snowpack ripening, which again is right prior to runoff onset, is something that looks pretty doable. And especially with the optical data, I think we have a good shot in producing some pretty good results. So down here at the end, I just have my acknowledgements. I'd like to thank my friends and family. It's been a tough year, but everyone's been really supportive of me, so I appreciate that. And I have some wonderful lab mates who encourage me and keep me doing this stuff. So I really appreciate everyone. And if you're here right now, if you're watching this, I really appreciate that you've taken the time to come to my poster. It's my first time presenting anything, and it's been fun. So again, I really appreciate everyone. Thanks again for coming.